we are going to have the second course of Javier Ribon, who is explaining to us why we should think of germs of diffeomorphisms as linear algebraic groups.
Yes, yeah. So something that I realized yesterday after the talk is that I didn't explain very much why this is connected to foliation theory. So there are problems in foliation theory in which you have naturally local diffeomorphisms. For instance, if you consider the holonomy group of a leaf, even if you're working in a global setting, this is typically a group of local diffeomorphisms. So, and you want to understand, I don't know, for instance, the integrability properties of a foliation, you end up studying the transversal structure, the holonomy group, and there you have that, in general, this group is, for instance, if the leaf is compact, is a finitely generated group of local diffeomorphisms. And so what we are trying to do here is to give to these groups, for instance, the holonomy group of a leaf, that you can see as a group of local diffeomorphisms. N would be the codimension of the foliation. 0 here, this indeed is a transversal. This is the point of intersection with a transversal. What you want to do here is give to the group, I don't know, let's call it G, to give some more structure, to make this group bigger in some sense, or to make it bigger. So, yeah, in this way we are going to get a group that is going to contain other elements, because the way of giving a structure is extending the group. So you're going to have elements that are not going to be, for instance, if you're studying the holonomy of a leaf, you're not going to have elements that don't correspond to the holonomy along any path, on the one hand. But this further structure can be useful to understand the properties of the original group. And in particular, a technique that you can use several times is when you go, for instance, in our setting to the Zariski closure, you can define, I'm going to talk about this soon, the Lie algebra of the Zariski closure. And in that way, you get an object in which you are somehow linearizing the initial setting. And that it's much simpler to deal with, this Lie algebra, than the initial group for certain problems at least, or that the Zariski closure. And this is going to consist of formal vector fields in our settings, so we end up needing to understand in order to, for instance, to understand the classification of these Lie algebras in certain cases, or the actions that, the adjoint actions of diffeomorphisms in these Lie algebras, we need to understand the intimate properties of the formal vector fields in here, and for instance, what kind of integrability properties have, first integrals, and so on. So that's the way in which we end up with something that pertains to the study of vector fields, foliations, and so on. Okay, the last day, or the first day, I was talking about this group TK, which is, there are several ways of defining this. I want to remember this. Is the group of K-jets of diffeomorphisms, right? And you can, and we were interpreting these K-jets as linear maps from the maximal ideal of the ring of formal power series over its k plus 1 power in itself. Yeah, and this is the map that sends the class of a function or a formal power series, if you want to be more precise, to the class of the composition by phi. And we said that this obviously is a subgroup of the linear group, but it does not contain every element in the linear group. And indeed, it's the same thing as the elements of the linear group that are morphisms of this C algebra. Okay, I'm going to write this condition so that it's clear. And this should happen for every f and g in the maximal ideal. You have that these two things are the same. That's if you want a theorem, a simple theorem, but it's an interesting result. In this setting, we can define the heuristic closure of a group of local diffeomorphisms or formal diffeomorphisms. The definition is going to be the same, right? And what we are going to do is considering for every k the subgroup induced by the k jets of elements of G, right? This is very easy to see that it's a group. Sorry. It's a subgroup of this group over here, which is a linear algebraic group. So we can consider the closure, and the result is going to be still there. So it's going to be, still the elements are going to be induced by the action of diffeomorphisms. So you consider the closure, and you define the Zariski closure of G in this context as the inverse limit that indeed is a projective limit of the G case. So it's the set of, but it ends up being a group, okay, of formal diffeomorphisms such that the k jet of phi is in the closure of the gk for every k. Okay, we have.
You want to write gk bar, right?
Yes, you're right, exactly. Thank you very much. Yes, otherwise we could get the initial group. And what we want is to see some properties of this definition, what we can get. In particular, this, the dimension of these closures is well defined, of course, because they are linear algebraic groups, and it gives you an increasing sequence. It can stabilize at some moment, it can stabilize, and then you can say that the closure has finite dimension, or it can go to infinity, and then the closure has infinite dimension. Okay, so this is the setting. Yes, something. So we can say that a subgroup of formal diffeomorphisms is Zariski closed, for instance, or another definition that, or another term that you can use is pro-algebraic, because it's a projective limit of algebraic groups, if it coincides with its closure. So something that you could actually ask at this point is whether we have an example of, I don't know, a Zariski closed group, because the definition is so far quite abstract. And a remark is that if you have some property, invariance properties are defined in general this kind of Zariski closed groups. For instance, imagine that you consider a formal power series. I think I used this notation the other day. you have a formal power series in n variables, or a function, whatever you prefer. And you defined the following group, the group of formal diffeomorphisms. As I say, it's easier. You can define the group of, if the function is analytic, you can define the group of analytic diffeomorphisms that satisfy the condition that I'm going to write down, but working in the formal setting is a little bit easier. So that you have that phi preserves F. This defines a group. Well, that's pretty obvious. But it defines a Zariski closed group, because if you write this equation over here, you can, this is going to have a Taylor series expansion, this is going to have a Taylor series expansion too. You consider the quality of every coefficient in the Taylor series expansion, that's going to give you algebraic equations in the coefficients of phi. And so every single time that you are in that situation, you have a pro-algebraic group. So groups that are defined by polynomial equations in the jet spaces are Zariski closed. Right? Here, if you, for instance, consider, I don't know, a term, a coefficient of degree 2 here, the equation is going to depend just on coefficients of phi of degree up to 2. So here we have infinitely many variables because phi lives in an infinite dimensional space, but every of the equations that are induced by this equality depend just on finitely many variables. And that actually provides the algebraic nature of G. Okay, so we are going to go back to this example in Zoom. And what I wanted is to talk a little bit about concepts in the theory of linear algebraic groups that generalize pretty well to the case of local diffeomorphisms. So you have, if you are working with the linear group, yeah, subgroups of the linear group, I mean, you have the closure of G is an algebraic set, it's an algebraic manifold with finitely many irreducible components, right? So you have that this group over here is normal in the Zariski closure no matter what, always, and that this index is finite. And I don't know if there is, you have another property that it's interesting in the theory, is that whenever you have a subgroup H of G that has finite index, then necessarily its closure contains the connected component of the identity. So for the closure, the smallest group of finite index is this one. I don't know, those are very, very classical results for linear algebraic groups. You can find them in any book. What you're gonna have, I don't know, so wait a minute that I don't say. Yes, how do you define this connected component of the identity in the case of local diffeomorphisms? You could try to define a topology or to consider the natural topology in the inverse limit, but we are going to try to do it in an inverse limit kind of way. We are going to say that those are going to be the elements in the Zariski closure such that the K-jet, instead of being in this closure, it's in its connected component of the identity. For all K. That's gonna give you a subgroup of the it's gonna give you, because if it happens in every jet space, it's very easy to see that this connected component of the identity, it's a terminology because we didn't introduce any topology. It's normal in the closure, in the Zariski closure of G. But are these properties still true? For instance, if you have a finite index subgroup of a group of local diffeomorphisms, is it still true that the connected component of the identity is contained in the closure of H? Let's see. Another thing that you can define for linear groups is obviously the Lie algebra. We already defined yesterday. In the case of formal diffeomorphisms, what you're going to have is that this is going to be the Lie algebra of formal singular vector fields such that the one parameter group, induced by them is contained in the closure of G. So that the t-time map of X is contained in the closure of G for every t. And there are properties that you recover that are similar to the properties of Lie groups. For instance, something that we have is that if you have a group of diffeomorphisms, formal or not, formal or analytic, I mean, you're going to have that this connected component of the identity is actually generated by the exponential of elements in the Lie algebra. That happens in the exact same way that it does for Lie groups, or obviously for linear algebraic groups. Linear algebraic groups are Lie groups. So we're going to have a Lie algebra, and we're going to have a Lie correspondence. So in some sense, the theory is, I don't know, it's getting to a good place. We are not just defining things for the sake of it. And what I wanted to say now is some properties that we already know for, because I would like to give a little case in which calculations are simpler. When you consider, and the ideas are simpler, and for instance, if you have a linear operator that is unipotent, that's a case that we like because it's possible to calculate everything. So what things are you going to have? We already said yesterday that if you consider the Zariski closure of the group generated by A, this is going to be the one parameter group induced by the infinitesimal generator of A, which is the unique endomorphism that is nilpotent and whose exponential is A. Since clearly this group is connected because it's C. In this case, you have that this closure coincides with its connected component of the identity. And obviously, the Lie algebra in this case, it's written over there, right? It's just the complex multiples of the infinitesimal generator. What's going to happen is that if you change here the setting, and instead of considering a linear operator that is unipotent, you consider a diffeomorphism, formal diffeomorphism, such that it's unipotent, and I remind you that this means that the linear part is a unipotent linear operator, then everything works the same. You consider here phi, here logarithm of phi. When you consider here the closure of the group generated by phi is the same as its connected component of the identity, and here you just change A with phi, you replace A with phi, and all these results are the same. So in this way, we have more examples, maybe not many very difficult, but more examples of pro-algebraic groups. Every group, every one parameter group induced by an nilpotent vector field is going to be Zariski closed. Of course, a priori, this group can be very big. I don't know. For instance, it's very big if f is a constant, and that group is not that very big, this one over here, because the dimension is 1. But yeah, both of them are Zariski closed. Okay, if you have an element, okay. What you have is that its infinitesimal generator is always contained in the Lie algebra of the closure of G, and indeed A is in the connected component of the identity. That's not difficult. I don't know. It's if you have A, the closure of A, the connected component of the closure of A is going to be contained in the connected component of the closure of G, and because of this coincides with the closure of the group generated by A that contains A. And since all these diffeomorphisms are contained in there, then the infinitesimal generator is in the Lie algebra. So that happens every single time. When you have unipotent diffeomorphisms, they are always in the connected component of the identity of the closure of your group, and their infinitesimal generators are always in the Lie algebra. And again, this happens if you write here formal diffeomorphisms and you replace here A with phi. Both properties are still true. They're very, very natural. Another remark that I wanted to make.
Excuse me, don't you need unipotent diffeomorphism?
Yes, you're right. Thank you. Yeah, for sure. Otherwise it's not true in general. But yeah, you're right. It's true if you have this condition over here, but that condition in the non-unipotent case is non-automatic. So if you have this is not a group, so this is an abuse of notation because you can multiply unipotent operators and the product can be non-unipotent, but it's an easy way to write this. So if you have that G consists of unipotent operators, the same thing happens for its Zariski closure. This is because being unipotent is given by an algebraic equation, which is this one. So if it's satisfied by the elements of the group, it's satisfied by the elements in the closure. And in particular, that implies that you can actually write down the closure of G in the following form. You consider the union for the elements of in the closure of the connected components of the identity of the cyclic groups generated by them. of the closures of the cyclic groups. And this is clearly true because this thing over here contains A, and because of this. A belongs to this, that belongs to this. So it's clear that the right-hand side is contained in the left-hand side, and the other inclusion is pretty obvious. And so you get that this group over here can be written as the union of connected sets that have one point in common, that is the identity element. So this is connected. So you have that groups generated by unipotent linear operators are always connected. And this, again, happens in the same way if you consider groups of unipotent formal diffeomorphisms, right? You end up with the same result. The connected component of the identity of the closure coincides with the closure. All these results work very well in all these situations. Okay. Something that we didn't say yet is whether it's not difficult to prove, as I said, that the connected component of the Zariski closure is normal. That's because in every jet space, this is a normal subgroup of this one, of the Zariski closure of GK. But it's the index finite. Here, you can see something. I wrote this to convince you of a property without doing a proof. Here we have that the Zariski closure coincides with its connected component of the identity. But you can see that this property over here depends just on the linear parts of the elements of G. What happens besides the linear part doesn't matter, because being unipotent means that the linear part is unipotent. It's a condition on the linear part of every element. So we have a condition over here on the linear part of G that guarantees that you have this equality, that the Zariski closure is connected, right? So this is still true for the case of diffeomorphisms. What you can actually prove is that the group that we defined, we asked here that the K-jet should be in the connected component of the identity of the closure of the group of K-jets of elements of G. There are infinitely many conditions. It suffices to consider the condition for K equal to 1. This is a result, it's not proposition. So in particular, whether or not a group has a connected Zariski closure depends just on the linear part. Because obviously, this depends on G1, that's the one jets of elements of G. Okay, and what happens is that the group, the connected component of the identity, in this case, for G, a subgroup of the group of formal diffeomorphisms, is indeed a finite index subgroup of the Zariski closure every time. But this is, sorry, because I'm not going to prove here this, but this index is indeed the index of the connected component of the identity of the closure of G1 in that closure. And obviously, you are working here in a finite dimensional setting, so this is finite. So you still get that you have the Lie correspondence, And you have that this group over here continues to be of finite index in the Zariski closure, even if this group is infinite dimensional. If this group is infinite dimensional, this one is also infinite dimensional. But the index is always finite. And what else? And the other property that you have, for instance, is that if you have, again, let's consider a subgroup of formal diffeomorphisms, and you consider a normal subgroup of G of a finite index, then you're going to have that the index of the closure of H in the closure of G is still finite, and it's indeed less or equal than the index of H in G. Yeah, that's not very difficult to prove. In particular, there is another property that I didn't write down, but another thing that happens too is that the connected component of the identity of the closure is contained in the closure of H. So again, you have that the minimal group of finite index of the Zariski closure is its connected component of the identity. That's still true. Okay. Another thing that I would like to give some applications of this, not just introducing the theory. So something that happens too is that the closure has, in some aspects, a similar algebraic structure as the initial group. For instance, if you have that G is abelian, this doesn't matter where you're working. You can be working in the finite dimensional setting or in the infinite dimensional setting of formal diffeomorphisms. But what you have is that if G is abelian, if and only if, its Zariski closure is abelian. And similar properties happen for other properties. You have G is nilpotent if and only if the closure is nilpotent. G is solvable if and only if the closure is solvable. G is metabelian, whatever that is, if and only if the closure of G is metabelian. All these properties work, and it's not difficult to convince yourself that this should happen. For instance, what it means to be abelian. G is abelian. I'm going to give an idea, all right? If and only if the commutator of F and G is the identity element for every pair of elements of G, right? The commutator, if people don't remember, is this expression over here. That is the identity element if and only if the elements commute. So, okay, suppose that you have that G is abelian, and you have this expression over there. If you fix G, it's polynomial in F. As I said in the first talk, the inverse is a polynomial map in this with the conventions that we make. So it doesn't matter here that you have the inverse. It's polynomial in the coefficients of F. We are adding as a polynomial variable the inverse of the determinant. And if you fix F, this is polynomial in G. So since you have, you fixed G, and what happens is, since this is polynomial in F, and vanishes for every F in the group, it vanishes in the Zariski closure. So you have that the commutator is going to be trivial for every F in the Zariski closure and for every G in the group. And now you fix F, and this vanishes for, or it's equal to the identity, for every element in the group. So it does for the Zariski closure. So if you have that two elements of the group commute, that any two elements of the group commute, the same thing happens for the Zariski closure. So it's abelian. And you can play this game with any other algebraic property, for instance. Obviously, you can try more sophisticated proofs, but as I said, I try to convince you that this is not difficult at all. Okay. So you are considering a larger group, but for instance, if you're interested in knowing whether the group is or not a billion, you can study this instead of this. You can study the Zariski closure instead of the initial group, and the Zariski closure, it's interesting because it has a Lie algebra, so you have something that is simpler to deal with, and this Lie algebra generates this group, the connected component of the identity of the closure, which is not the closure, but it's a finite index. So you are able of simplifying a lot some problems. Okay, I'm going to give a very simple application. Something that I forgot to say is if I remember that we said if you fix F, that is a formal power series, you can consider the Zariski closed group of the formal diffeomorphisms that preserve F. Right, we already introduced this element over here. Sorry, yeah. This is a group, this is a Zariski closed group. And you can calculate its Lie algebra. It's not going to be difficult because the Lie algebra in this particular case is going to be it's going to be geometric, of course. It's going to consist of the formal vector fields whose one parameter group actually is contained in G. So that you have that the time T map of X composed with F is equal to F for every T in C. Obviously, this is, obviously, I'm going to explain why, but let's say more than obviously, it's not difficult to see that this is the set of formal diffeomorphisms such that F is a first integral of X. If you want, going from there to there is derivative. Since the numerator is always 0, of course the limit is 0. So if this happens, this happens. If the one parameter group preserves F, the F is a first integral of X. And the other direction is the formula of the exponential. It's so exponential of X composed with F is F. X of F is 0. X applied 2 times to F is also going to be 0 because X is X of 0 and so on. So these two things are equal, and this is the Lie algebra. So we can calculate, in this case, essentially everything. And now the application, consider M-formal power series and we are going to assume that they are independent in the sense that I'm going to describe now. We are going to consider the wedge product of their differentials and we are going to assume that this wedge product is not identically 0. It is not never vanishing. It can have, I don't know, it can vanish in a codimension 1 set or whatever. But it's not identically 0. And now,
That actually vanishes in codimension. The term.
Yeah, you're right. Yeah, obviously, you're right. Well, unless the determinant is a unit, but yeah. Yeah, or it vanishes, or in the, it's the anticept or a codimension one set. So consider here the set of formal diffeomorphisms such that they preserve every single one of these functions. An application of these results that we were just talking about is that this group is finite. You can say, but this is so theorem, even if it's G is finite. You can say, but this is more or less clear, right? For instance, if you consider F1 equal C1 to the power 2, F2 equal C2 to the power 3, and so on. Yeah, obviously, the sets in which all these functions, the m functions coincide is going to be finite, so the group has to be finite. Yeah, sure, but we want to prove that doesn't have to rely on understanding these functions or anything. We want, and it works also in the formal case, for instance. And the proof is going to be very simple because the Lie algebra of this group that is Zariski closed because it's given by, if you want the intersection of n Zariski closed groups, it's going to be the intersection of the Lie algebra associated to every fj. So it's going to be the Lie algebra of formal vector fields such that x of fj is equal to 0 for every j. And precisely here, of course, if you're, I don't know, I'm going to write it down, even if maybe it's trivial for you in coordinates. This condition over here is the same as saying that the Jacobian matrix of F times the vector of components of X is the zero vector. These and these are equivalent, and precisely this condition is the condition that implies that this determinant is non-identically zero. So because of that, the unique solution to this set of equations is the trivial vector field, right? Okay. So what you have is that the Lie algebra is trivial. Now you have that the connected component of the identity of the Zariski closure is generated by the exponential of the elements in the Lie algebra. So it's trivial too. And that this group over here is a finite index in the group G, right? Here I don't need the closure because this group is already closed. So we have also this. And since G0 is trivial, G is finite. So, okay, it's a very simple proposition, but the idea is we are able of proving this without doing calculations. We don't have a proof in which we have to study different cases for the FJs. I think it's interesting, even if the result itself it's not going to win any prize. Okay, I think that I wanted to say other things. Something that, for instance, you can actually consider, I don't know, the origin in Cn, and here an analytic set with several irreducible components. right? This would be the components of the analytic set. And something that you can do in here is consider a group that actually, suppose G is a group of diffeomorphisms, formal diffeomorphisms that preserve S. Something that it's going to happen is that if you consider now the subgroup, I don't know, H of the diffeomorphisms in G, such that they preserve more than S. They preserve every reducible component of S. It's different. Preserving S means that, for instance, this branch over here could be sent over here, and this over here, and so on. Preserving every reducible component is fixing every single one of them. Not point-wise, okay, but fixing every single one of them. And what happens is that H is, of course, a finite index subgroup of G. It's indeed a finite index normal subgroup of G. That's very easy to prove. And what happens is that if the group G has a connected Zariski closure, these two groups are equal. So you're going to have results in which preserving an analytic set is going to be equivalent to preserving every reducible component. Because what happens here is that, as we said, the index of the closure of H in the closure of G is smaller or equal than the index of H, which is finite, but now this is a finite index normal subgroup of the closure of J, so it contains the connected component of the identity. This happens every single time that you have a finite index subgroup. This is general. But now, if you assume that your G has a connected closure, then you have this. And so all these groups are equal. So in particular, this group over here, again, it's easy to see that it's given by polynomial equations in the jet spaces. It's closed, sorry. And what you're saying is that G is contained here, because the closure of G is the closure of H. So in particular, in that case, G is equal to H. And this condition, for instance, we already saw that happens if G is a subgroup of unipotent formal diffeomorphisms. So, for unipotent formal diffeomorphisms, phenomena in which you have periodic objects become phenomena in which you have fixed objects. And again, you don't need a very lengthy proof to show this. And it doesn't depend very much on the phenomenon we are studying. It depends on the fact that these two groups are the same, and that the action that you have in this set is indeed a quotient of these two ones. And when they are the same, this quotient is trivial. If the quotient is small, you're going to get that the action is going to be simple, but not necessarily trivial. How much time do I have?
5 minutes or so.
Oh, 5 minutes, okay. So you have very, very simple applications of this. But interesting anyway. I mean, I think that in these simple applications, you can see that we were spending the time in a good way because you can see that this can be applied to a variety of problems. Okay. The result that I wanted to give another application a little bit more sophisticated. Obviously, I'm not gonna, I wanted to give two. But there is a result by GIS that says that if you have, I wanted to give applications that are not living in the group of local diffeomorphisms, so that you see that you can work with this. You don't need to say, oh, I'm going to work in this. These applications appear in other contexts. So for instance, there is a result of GIS, a theorem, that says that if you have a group of real analytic diffeomorphisms of the sphere, right? It's a global thing, it's not local anymore. And this group is nilpotent. And I think that's it. Then the group is metabelian. Okay, I'm going to explain what is metabelian. Maybe I should explain what is nilpotent too. Nilpotent, when you have a group, you can associate several series of subgroups.
You want to say that G is metabelian or that you choose to be?
Ah, yeah, sure. Thank you very much. Yeah, yeah, what you said, yeah. This is the same as G2 is trivial. Yeah, it's I made a mistake. But so there are different series associated to groups. One of them is the derived series. Another one is the, for instance, descending central series. So you, by definition, decide that the first, the element of level 0 in the series is G. The element of level 1 that is also called the derived group, I'm going to define these two ones that are the same. So, is the group generated by the commutators. The commutators don't necessarily, the set of commutators is not necessarily a subgroup, so we have to consider the subgroup generated by them. Right? And once you have the first one, the k plus 1 is the group generated by commutators of the form Fg, where F belongs to the kth element in the descending central series, and G is an element of the group. These groups are, if you want, the groups that are the closest, very roughly speaking, to be abelian without being abelian necessarily, right? Of course, every abelian group is nilpotent. But these groups are interesting, for instance, because the center is never trivial. You have always non-trivial elements in the center, provided that the group is non-trivial, of course. And you say that it's nilpotent, by definition, if there exists some k such that the group is trivial. Okay? For instance, if you, I don't know, here, if you remember something about your courses of...
Now we have 5 minutes.
Okay, so I'm going to finish. But I'm going to say something very quickly. If you remember your group theory, there is a result that says that if you have a group that has p to the n elements, where p is a prime number, then it's always nilpotent. This is a consequence of the Thil theorems. And okay, next day I can start with this. The other thing that I wanted to define now is what is metabelian. That's easy. The second derived group is by definition just the derived group of the derived group. So you're saying the derived group is trivial if your group is abelian. So okay, if it's not abelian, if the derived group is itself abelian, you say that it's metabelian. Okay, it's just a definition. But the point here is that the interesting part of this is that you could actually, for instance, ask, okay, I want to realize an important group as a group of real analytic diffeomorphisms of the sphere. Can I do this? Is it always possible to have a faithful representation of that group? And the answer is no, because you can see here that the fact that can be interpreted as one of these groups implies that it's metabelian, and not every nilpotent group is metabelian. So you're going to have some restrictions, and next day we can discuss this.
Questions, comments?
Questions?
Comments.
So just one question. In the statement of the theorem of Gis, metabelian does not mean that the sequence stops, the nilpotent sequence stops at step 2. No?
No.
That's true?
No, no, there are, yes, you can define an invariant for nilpotent groups that is the moment at which you stop. And that's the class of nilpotents. I think that's one way. There are people that say that if you step at level K, the group is a step K nilpotent. Mm. The point is, there are groups that are of class K for every K. So this series can be long, okay? But the group is metabelian because, of course, the group the G2, the second derived group of G, the one that is defined here, is much smaller in general than the second element of the central of the descending central series. So this is going to be trivial, but this is non-trivial, and indeed we cannot even say that, I don't know, the 10th one is trivial. It's going to depend on the group. For every K, there is a group of real analytic diffeomorphisms of the sphere that is a step K nilpotent.
Ah.
I can send you the examples if you want.
Exercise.
Okay. Thank you. Question?
And what about the converse of G's theorem?
I don't think that's... no, I don't know. I should think about it, but no, it's... no, that's not going to be true because the affine group is metabelian. So you can have... right? I'm not saying something... This group is a group of Möbius transformations of the sphere that is metabelian, because the derived group is the group of translations, but is non-nilpotent. So no, the other implication is it's much. Here we are actually considering the descending central series, and we are deducing something for another series that Yeah, but the information that gives you the descendant series is very strong. So we are going for a series in which, I don't know.
We are going to see tomorrow. So let's thank the speaker again. And I propose that we resume in 5 minutes.